Now we discuss some problems related to phase equilibrium. Predict the degree of freedom in the following systems: liquid water and water vapor in equilibrium. So here component is 1. So for problem 1, so component, a number of components C is 1, phases, number of phases P is 2. So F is C minus P plus 2. So F is the degrees of freedom. Degrees of freedom. So we get one component, 2 phases. So number of degrees of freedom is 1 here. Okay, so this is along this coexistence line. Okay, in the phase diagram. Then liquid water and water vapor at equilibrium. Again, this is, since P is 1 atmospheric pressure, since P is 1 atmospheric pressure and constant, so hence the phase rule F is C minus P plus 1, because as I mentioned in the phase rules, F equals to C minus P plus 2. This is the general phase rule. General phase rule. And this plus 2 terms comes from pressure and temperature. Pressure and temperature gives this plus 2 terms. So since pressure is constant, this plus 2 becomes now plus 1. Okay. And how many components? So liquid water and water vapor, again number of components is 1 here, but phases are 2. Number of component C is 1, number of phases P is 2. So F is 1 minus 2 plus 1, so we get 0. So there is no degree of freedom here. Next, problem 2 says, calculate the components and the corresponding degrees of freedom for the system's mixture of N2H2 and NH3 and mixture of CaCO3, solid, CaO solid and CO2 gas. Okay, so we are dealing with mixture of 3 gases here for first case. We are dealing with mixture of 3 gases. 3 gases. What are the gases? N2, H2 and NH3, right? So C is 3, but P is 1 because all are gases, so only one phase we get. Okay, so F. So degrees of freedom, number of degrees of freedom F is C minus P plus 2, so 3 minus 1 plus 2 gives you 4. So it says that temperature, pressure and concentration of two of the 3 gases, of the 3 gases or components need to be specified. Right. Second problem says mixture of CaCO3, CaO and CO2. So again C is 3, P is 3, right, because two solid phases CaCO3 solid and CaO solid plus one gas phase CO2 gas, right. So, F is C minus P plus 2. So, 3 minus 3 plus 2 gives you 2. So, meaning it says that temperature and pressure need to be specified. Now, the third problem is calculate the components and the corresponding degrees of freedom for the system Fe solid plus H2O gas is in equilibrium with FeO solid plus H2 gas. Here, how many components are there? Number of components. C is 3, right, like before. Two solid phases Fe and FeO, and phase is also 3 here because two solids plus one gas, right. Since equilibrium, since they are in equilibrium, so there only are one gaseous component. So, we write F is 3 minus 3 plus 2. So, we get 2. Next problem says calculate the change in vapor pressure of the water system if the temperature changes by 1 Kelvin. At 100 degrees Celsius, the molar volumes of water liquid and water vapors are 18 centimeter to the 3 per mole and 18 times 1673 centimeter inverse per mole respectively. The molar heat of vaporization of water can be considered as 40584 joules per mole. Okay, so given molar volume of liquid water is 18 centimeter to the 3 mole inverse, means 18 times 10 to the minus 6 meter to the 3 mole inverse. This is in SI unit. So, we are converting centimeter to the raised to the 3 to meter raised to the 3. So, molar volume of water vapor is 18 times, this is times 18 times 1673 centimeter inverse, centimeter raised to the 3 mole inverse. So, we get 18 times 1673 times 10 to the minus 6 meter to the 3 mole inverse. So, as per the Clapeyron equation, we know dp by dt gives delta H vaporization by T times Vg minus Vl. So, dt here, since dt equals to 1 and T is 273 plus 100, right. So, 373 Kelvin. So, we write dP is 40584 joule per mole times here dt was 1. So, 1 Kelvin, right. So, we write this by 373 times 30114 minus 18 times 10 to the minus 6. Okay. This is so if you carry out this one, we get 0.00361 times 10 to the 6 Newton meter to the minus 2. So, we get 0.0356 atmosphere. Okay, so, if you convert this is nothing but Pascal. So, from Pascal we can convert to atmosphere, okay, because 1 atmosphere is 1.01 times 10 to the 5 Newton meter to the minus 2 or Pascal. Okay. So, this is based on Clapeyron equation. Next, we move to problem number 5. It says if the vapor pressure of water is at 95 degrees Celsius is 634 mm and the vapor pressure of find the vapor pressure at 100 degree Celsius. Consider the molar heat of vaporization as 40584 joules per mole. So, here liquid is in equilibrium with vapor. So, from Clapeyron equation we know, from Clapeyron equation we can write dP by dt is delta H vaporization by T Vg minus Vl, right. So, if we do the differentiation, we get ln P2 by P1 is delta H vaporization by R T2 minus T1 by T1 times T2. So, if we do the differentiation, we get this expression considering ideal gas behavior and the vapor and the volume of liquid water is much smaller than volume of gas. So, and we consider the volume of gas behaves ideally, then we arrive at this expression. Okay. So, here T2 is 100 degrees Celsius. So, 373 Kelvin. T1 is 95 degrees Celsius, means 368 Kelvin, right, and P1 is given. P1 is 634 millimeter of Hg, and then P2 we need to calculate. Another thing is given is delta H vaporization is 40584 joules per mole. So, if we use this expression, we get ln P2 we need to calculate, P1 is 634 and delta H is 40584 in joule unit, and if we use, so we need to use R value of R in joule unit, so 8.314. So, T2 is 373 minus 368 and divided by 373 times 368. Okay. So, we get basically P2 is 759.2 millimeter. Thus, the vapor pressure of water increases from 634 millimeter to 759.2 millimeter of Hg when the temperature increases from 95 degrees Celsius to 100 degrees Celsius. Problem number 6 says the specific volume of water and ice, water means liquid water, at 0 degrees Celsius are 1 centimeter cube and 1.09 centimeter cube respectively. Calculate the change in melting point of ice per atmosphere. So dP is 1, okay, atmosphere increase in pressure. Molar heat of fusion of ice is given. So what are these things given? So answer is here given. V liquid is 1 centimeter cube, means 1 times 10 to the minus 6 meter cube. V solid is 1.09 centimeter cube, gives you 1.09 times 10 to the minus 6 meter cube, and delta H is given. So delta H is 6010 joules per mole, right. So we know dP by dt from Clapeyron equation we know dP by dt is delta H fusion by, this is delta H fusion here, by T times VL minus Vs, right. And we need to calculate, so what do we need to calculate? Calculate the change in melting point of ice per atmospheric increase in pressure. So we need to calculate dT by dP, right. So change in melting point dT of ice per atmospheric increase in pressure dP. So dT by dP is T VL minus Vs by delta H fusion. Now if we substitute all those values here, so T here is 0 degree Celsius. So T here is another quantity given, T is 0 degree Celsius, so means 273 Kelvin. So 273. Now volume of liquid is 1 times 10 to the minus 6 minus Vs is 1.09 times 10 to the minus 6, and delta H is also given, delta H is 6010 joules per mole. So if we do it, we get we get dT is dP is per atmospheric pressure. So 1 atmospheric per atmospheric. So dP is 1 atmospheric pressure. So 1 atmospheric pressure means 1.01 times 10 to the 5, right, 5 Newton meter to the 2. So dT by 1.01 times 10 to the 5 gives 273. We get the minus sign here, 273 times 0.09 times 10 to the minus 6 by 6010. So you get dt is minus 0.0075 Kelvin. So with per atmospheric increase in pressure, so the melting point decreases, right. So negative sign means the melting point of ice of ice decreases with increasing in pressure. That is what we observe from the phase diagram of water. Problem number 7 says the rhombic sulfur changes to monoclinic sulfur at 96 degrees Celsius and 1 atmosphere. Find the change in transition temperature per atmospheric change in pressure. Consider heat absorbed in the change is 2500 joules per mole and density of rhombic sulfur and monoclinic sulfur are 2.05 gram per centimeter cube and 2.05 grams per centimeter cube and 1.95 gram per centimeter cube respectively. So, from the Clapeyron equation, we can write dt by dp, we just discussed, T is Vb minus Va by delta H transition, right. So, B and A are two states, okay. So, Vb is the molar volume of monoclinic sulfur. So, what is the molar volume of monoclinic sulfur? So, it is 32 by the density, right. Density is 1.95, this is gram in gram per centimeter cube, centimeter to the minus 3. So, we get 16.41 centimeter cube, okay. So, we get 16.41 times 10 to the minus 6 meter to the 3. Now, what is Va? Va is the molar volume of rhombic sulfur. So, what is the molar volume of rhombic sulfur is 32 by 32 gram by 2.05 gram per centimeter cube. So, if we calculate, we get 15.61 centimeter cube, we get 15.61 times 10 to the minus 6 meter cube. So, it says rhombic sulfur to monoclinic sulfur, okay. So, the final state is monoclinic, this initial is rhombic sulfur, okay. So, that is why Vb minus Va. So, that is why we consider B as monoclinic and A as rhombic sulfur, okay. So, delta H, okay. So, delta H transition is 2500 joules per mole. Temperature is 96 degrees Celsius. So, 273 plus 96 gives you 369 Kelvin, okay. And dP is 1 atmosphere. So, 1.01 times 10 to the 5 Newton meter to the 2 minus. So, we get dt is 369 times 16.41 minus 15.61 times 10 to the minus 6 times 1.01 times 10 to the 5 by 3, delta H transition, right. So, delta H transition is 2500, okay. Okay, so if we do it, we get 0.011 Kelvin. Okay, this is the change. This is the change in the transition temperature. Okay, this is the change in transition temperature. Transition temperature. Okay, per atmospheric change in pressure. Next, we move to problem number 8. It says, as supercooled water freezes, the rise in temperature occurs to 0 degree Celsius. What is the source of heat for the process? H2O gas minus 10 degree goes to H2O solid at 0 degree Celsius. So, in this case, delta H is 0, right? No heat is transferred. To or from the system. The heat is liberated in the freezing process of water warms the system to 0 degree Celsius. So, H2O gas, supercooled water, so H2O gas phase in minus 10 degree Celsius, when so it releases some amount of heat to form water. Okay. So, that is why the heat liberated in the freezing process of water, when it freezes, warm the system. So, that is why the temperature increases to 0 degree Celsius.